Hi friends, now in this lecture we'll see the disadvantage of Nyquist second criteria pearls or Nyquist second criteria and the remedy how to overcome this disadvantage. So what is the disadvantage of Nyquist second criteria? The disadvantage of Nyquist second criteria pearls is that whenever 0 occurs in the sampling instant, as we have seen in the previous lecture also, at the sampling instant if it is 0, then the detection is based on the nature of the previous bit. If my previous bit is 0, then it has to be 1. If my previous bit is 1, then detection of the current bit has to be 0. So the just inversion has to be there. The problem is that if error occurs in this previous bit, then this bit or this bit will be in error. Now, so there is a dependency of the detection of the current sample if my sampling instant is 0. Now, how to remove this dependency? How to remove this dependency? My decision rule should be such that it should be based on, my detection should be based on the value of the current sample, not on the nature of the previous bit. So how to remove this dependency? The solution is given by something which is called as differential encoding. So differential encoding is a scheme by which we can remove the dependency, and the procedure is this. We'll show that dependency is not there. So we will show that also. So this is the arrangement of differential pulse code, differential encoding, and this is my information bit. This is scheme that will produce differential encoding, and this scheme is basically for producing Nyquist second criteria pulse. So how this particular differential encoder works? So that the sample values which are 0, the decision at the sample value that is 0 is independent of the nature of the previous bit. That we'll see now. Let us consider this information bit, that is 1 0 1 1 0 0 1, which is present here 1 0 1 1 0 0 1. Now what we need to do is modulo 2 XORing is to be done with the output of this differential encoder, and initially my flip-flop, that is a D flip-flop, is in reset state, that is 0. So 0 and first bit are to be XORed, so output is 1, because XORing means when two bits are different it will generate 1, if two bits are same it will generate 0. So as can be seen, my reference bit and this bit will produce 1, and now after a 1 bit delay this 0 will come at the input, and this 1 will come at the input of modulo 2 adder. So in the next clock there is to be XORing of this 0 with this 1 as is shown here. So this 0 and this 1 is to be XORed, result is 1. In the similar way, this 1 and this 1 is to be XORed, result is 0. And this 0 is to be XORed, result is 1. This 1 and 0 XORed, result is 1. This 1 and 0 is to be XORed, result is 1. And this 1 and this 1 is to be XORed, result is 0. So this way we have received this particular bit. What is this? Is the output of your differential, that is output of your differential encoder, differential coder, which is actually your PK. Then after we are using polar signaling. So polar signaling means corresponding to 1 we will use +1 volt, corresponding to bit 0, we will use -1 volt. So as is shown here, this is my reference bit. So 1 volt, 1 volt, 1 volt. So corresponding to 0 bit, I get -1 volt, 1, 1, 1, -1. Then after, we have sampling instant. At sampling instant, what is the value is the important question. So what we do is, in the similar fashion that we have seen in the detection of Nyquist second criteria pulse, this is, what is this? This is a sample value. This is -1 actually. So sample value is -1. Since we are using Nyquist second criteria pulse, that is why these two would be added together to produce this sample value, which is 0. These two will be added together to produce this sample value, which is 2. In the similar way, 1 and -1 will produce 0, and -1 and 1 will produce 0, because we are using Nyquist second criteria pulse, in which two pulses interfere with each other, and the sampling strength, level of the sampling strength is decided by the value at the adjacent value of the adjacent pulses. And in the similar fashion, we have 1 plus 1 gives 2, 1 plus 1 gives 2, and 1 minus 1 gives 0. Now we have to devise detection. What is this? These are the sampling instant. We have to devise detection scheme or detection rule, so that the bit which is detected at the receiver is same as the transmitted bit. And this is a decision rule which is defined. So if I use this rule, that is, whenever I encounter 0 volt, the decision will be taken in favor of bit 1, and whenever at the sampling instant I encounter plus minus 2 volt, then decision will be taken in the detection of 0 bit. If I use this rule, then let us see what happens. So I'll start from here. Because the first is my reference bit. I'm not interested here because my information bit will start from here. So first, this is 0, case 1, detected bit is 1. Then it is 2, case 2, detected bit is 0 as per decision rule. Then 0, which is a case 1, detected bit is 1. Again 0, detected bit is 1, 2, 0, 2, 0, 0, case 1, detected bit is 1. So in this decision rule, what is the beauty of this decision rule is that in this case, detection of the bit in any of the level is not depending on the nature of the previously detected bit. That is why, in other words, there is no dependency on the previously detected bit, as was the case in Nyquist second criteria. So this dependency has been removed by the scheme which we call here as differential encoding. That is why this is the advantage of this scheme, that is differential encoding. So in this way, it can be shown that if you use differential encoder, then the disadvantage of Nyquist second criteria can easily be removed. This is what we started with we intended to cover in this lecture. Thank you.